Good evening. I'm John Hubbard Jr. As the other John said, I'm Vice President of Geologists at Jackson Hole. I'd like to welcome you here tonight on behalf of both the geologists of Jackson Hole and the Teton County Library, without whom this program would not be possible here. I'd like to ask everybody to pull these things out and turn it off or put it on vibrate or something silent. I was sitting right here at a program a week ago, and the lady's phone went off twice. She didn't seem to know how to turn it off, so shout if you need help. It was very obnoxious and very inappropriate. So I'm just going to ask you to do that here, because I had a pretty strong lesson in that just here very recently. Tonight, we are very fortunate to have Dr. Dan Dzurisin here with us. He is research geologist at the U.S. Geological Survey, the USGS Cascades Volcano Observatory. He has a bachelor's in physics from Notre Dame, a master's and PhD in planetary geology from the California Institute of Technology. He was a staff member of the USGS Hawaiian Volcano Observatory from 77 to 81, and since that time has been a staff member at the USGS Cascades Volcano Observatory, where 94 to 97 he was the scientist in charge, and since 1983 he's been a project chief with the USGS Volcano Hazards Program, which means he gets to travel a lot of interesting places around the world. I want to talk to him later about PhD, where I lived for a couple of years. He's the author of over 100 scientific papers, publications, over 100 abstracts. His current research is directed towards understanding volcanic unrest using various geodetic techniques, of which I'm sure he will talk some about here tonight. He studies crustal deformation in the Cascade Range, the Aleutian Volcanic Arc, Hawaii, and not surprisingly, and not least of all, Yellowstone. So I'd like to ask you to join me in welcoming Dr. Dan Dzurisin.
Thank you, John. Let me start by asking if folks in the back can hear me. Is the mic working okay? I see thumbs up. I'm going to wander around a little bit as we go through the talk. I might spend some time over at this podium as well, because I want to be pointing at the screen, and when I point at the screen, I don't want to turn my back to you. So I might be over at the podium for a bit. Thanks to John, and John, of course, for the invitation to come talk to you tonight. Thanks to all of you for coming. It's awfully nice out there to be inside. I wouldn't be if I wasn't giving the talk, to be honest. But thank you very much. I want to thank also Peter Ward, who has been our host at his home with a spectacular view of the Tetons last night and tonight. He's been very gracious. It's been fun talking to him, learning a little bit more about you and geology and everything else that goes on in Jackson. So we'll spend about an hour talking about this topic. But before I get into the talk, I want to admit that I was a little apprehensive when I was first asked to give the talk. I was asked by a colleague and a mentor of mine, USGS mentor, Bob Killing. I understand he's a member of your group. Bob wrote to me and asked if I would be interested in giving a talk to the geologists of Jackson Hole. And I hadn't heard of your group. And my very first thought was, geologists of Jackson Hole. It sounds like a high-end group of outlaws. And I figured out that I was thinking of a hole-in-the-wall gang. And I thought, geologists of Jackson Hole, yeah, they'd be pretty smart, they'd be educated, they'd know where all the gold was, right? Because they're geologists. They know all the faults in the security system. We'll get that in fun. And I thought, gosh, this could be a difficult audience. And so I prepared my talk with that in mind. I have to say that the hospitality I've seen so far makes me think that that's not really the right characterization of you folks. Very friendly. And my talk's going to be pretty darn informal. I'm going to summarize what I've been doing in Yellowstone for the last 3+ decades. And I enjoy it. I enjoy the work. I'm fortunate to be able to do it. And I hope you'll enjoy it as well. I will point out my wife in the audience, Lynn, who's also shared Peter Ward's hospitality. She gets to come along with me on these trips. We get to Yellowstone 3 times a year, usually. Spend a lot of time in Jackson. Enjoy your wildlife, enjoy your scenery, enjoy your weather. We had an introduction this morning with a lightning and thunderstorm, followed by some wind and hail. And then the skies cleared and we had sunshine. And we went out and photographed moose everywhere. Everywhere we went. And it was really very nice. So, here's the question I pose to you. What's really super about Yellowstone? Now, of course, what I'm alluding to here is Yellowstone's characterization as a supervolcano. If you pay attention to any television, you've heard that Yellowstone is the world's premier supervolcano. So, what's super about it? Sorry about that. I'm a ground deformation guy. I study geodesy. So the answer to this question from my perspective is what's really super about Yellowstone is that it moves. It moves up and down, it expands, it shrinks, and we're able to measure that. It's a very, very dynamic place. And just in the course of my career, we've learned a tremendous amount about how that works. We knew relatively little about it when I started. We know a lot more about it now. But as you might guess, we still don't have the final answer. And I'm going to talk about how we might get that final answer a little bit as well. So, I thought this might be an appropriate slide for a group of geologists who've been known to frequent the local pub. And of course, it ties in with the characterization of Yellowstone as a supervolcano. You know, some folks worry about the supervolcano. And the best antidote to worry, of course, is, oops, have a beer. I thought that might be a good introduction to talking to geologists. So I'm going to talk historically about what we've come to know about Yellowstone and how it moves. And that story starts, of course, in the early expeditions. Way back in the late 19th century when folks first came out to Yellowstone and began to explore, the Hayden expedition, of course, began to talk about the remarkable geology out here. I wasn't around quite that long ago, but I have been around since the first really serious geologic studies of Yellowstone that were initiated by Bob Smith. I'm sorry. I'm getting to Bob Smith, he's the seismologist, but Bob Christensen. Bob Christensen did the geology here starting in the 60s and has spent 4 decades understanding the geology of Yellowstone National Park, understanding the rich volcanic history, and getting that information out to the scientific community and to the public. Of course, in parallel, Bob Smith, who's one of your members, has been working on Yellowstone, on the geophysics of Yellowstone. And the two of them together put together a pretty remarkable story about Yellowstone and how it works. This is Chris's professional paper, 729G, in which he talked about the geology of Yellowstone. Still a classic. We've learned more since then, but basic facts are here. Now, as you all know, Yellowstone it's the crown jewel of the National Park System. It's a World Heritage Site. Lots of scientists come here every year to do multidisciplinary research, and it's also the world's iconic supervolcano, for better or worse. What is beneath that title, beneath the title of supervolcano, is a living magmatic system called the beating heart of an active volcano. Yellowstone is an active volcano by the definition that some of us use. It doesn't mean that it's erupted recently, it doesn't mean it's going to erupt very soon in the future, but it's active. It's as active as it has been at any time, probably over the last few million years. It's just behaving on its own time scale. And it's time scale for eruptions is a few 100,000 years to a few million years. We can get around to it in its own time. In the meantime, we'd like to learn a lot more about it. What makes it tick? Tom Jagger was the first scientist in charge at the Hawaiian Volcano Observatory, where I spent the first 4.5 years of my career. Jagger visited here in 1922, and he said, anyone who has spent summers with pack train in a place like Yellowstone comes to know the land to be leaping. Mountains are falling all the time by millions of tons. Something underground is shoving them up. Of course, what's shoving them up is a combination of tectonism and magnetism. And the rest of the talk is going to focus primarily on magnetism. What's going on to cause Yellowstone to go up and down? Yellowstone makes lots and lots of earthquakes. This slide is from Bob Smith. It shows epicenters since 1975 in and around the caldera and the park. Hebgen Lake area out here, of course, the magnitude 7.5 Hebgen Lake earthquake in 1959. Bob has spent a lot of his career documenting the seismicity of Yellowstone Park and explaining to the scientific community and to the public concepts like the tectonic parabola. You see this parabola of hypocenters. Each red dot here, of course, is an earthquake, a historical earthquake. There aren't very many in here. It gives you the impression that something is different in here, and what's different in here, of course, is Yellowstone and the heat that fuels it from underneath. And as the North American plate drifts this way, that magmatic activity has disrupted the mountain chains that used to traverse across what is now the caldera, and the crust is still too hot to break. Most earthquakes happen because you're breaking rocks. And if the rocks are too hot, they don't break. They just move out of the way. And so Bob has done a tremendous amount of work documenting those processes and what the structure is beneath the park. Lots of earthquakes, lots of them in swarms. Now, I've looked at a different aspect of Yellowstone. I've looked at, not when I say Yellowstone is super because it moves, I don't mean it shakes. It's pretty interesting that it does that too, of course. I mean it moves more slowly. As I said, it goes up and down, and it stretches and it shrinks. It's been 40 years now since we first realized that Yellowstone can go up and down. Of course, there was the magnitude 7.5 Hebgen Lake earthquake that created Quake Lake. Then there was the 1975 Yellowstone Park earthquake near Norris, magnitude 6.1, major earthquake. The USGS and the University of Utah got together and said, we ought to go do some surveying to see how much ground movement there's been as a result of that 1975 earthquake. And so during the summers of 1975, 1976, 1977, University of Utah, USGS, did what are called leveling surveys on a sequence of benchmarks. You see in the background here, there's a 1923 benchmark. That was the very first leveling survey in 1923. They resurveyed all of those benchmarks throughout the park, 75, 76, 77, and they discovered a remarkable thing. The central part of the park had gone up since the 1923 survey, but, oops, I'll get this yet, by 726 millimeters, give or take, 70 centimeters. 70 centimeters is, what, over 2 feet. That's a lot of uplift at a volcanic system. And immediately, of course, people wanted to know why. Jack Pelton, Bob Smith published papers in Science and JGR in 79 and 81. And here's what they said in Science. They attributed that uplift, that 2 feet of uplift, to a recent influx of partially molten material to a location within the crust beneath Yellowstone National Park. The volcano was active. Magma had risen up beneath the park and shoved the surface up by 70 centimeters. Remarkable result. And that kind of launched what I consider the modern investigations, both geologic and geophysical, into Yellowstone National Park and what makes it tick. I came on the scene in 1983, back in the 20th century. There had been some large earthquakes. Well, first of all, Mount St. Helens had erupted in 1980, of course, on May 18th. Big, exciting time. Caused me to move from Hawaii to Vancouver, Washington, where I live now. All the volcanologists in the country and many international volcanologists were studying Mount St. Helens, and they were preoccupied. 1 week later, there were 4 magnitude 6 earthquakes in a place called Long Valley Caldera, California. And that was followed by a big swarm of earthquakes, and then in the succeeding months and few years, more earthquake swarms, and then a survey was done along a major highway, and they discovered that there had been uplift, something like 25 centimeters of uplift, as I remember. And we started getting asked the question, while we were working in St. Helens, what's going on in Long Valley? Is there any chance that place could erupt? So, discussions started, scientific discussions about what's causing the unrest at Long Valley. The guy who did the first detailed geologic studies in the park, the professional paper I showed you, got together with then branch chief Patrick Moffler, said, you know, Yellowstone has been doing everything that Long Valley is now doing for a long time, and he was probably thinking only better, but anyway, we should have somebody go study Yellowstone to try to understand better what might be going on in Long Valley. And so they allowed me to think that I came up with the idea, but in fact they established the project starting in 1983. And they said, why don't you go figure out, we know Yellowstone has gone up since 1923. Why don't you go find out if it's still going up the way Long Valley is going up now? And so we did something called leveling. I'll explain that in a minute, but it's an old-fashioned 20th century surveying technique. Here, of course, is the youngest caldera, 640,000 caldera. And we decided we'd simply level across it to see if the settled part was going up. We did that first in 1983, and then we repeated it in 84, 85, 86, 87. And what we discovered, we leveled, I can make that happen. No, not gonna make it. We leveled from Lake Butte, if you're familiar with Lake Butte, down near Yellowstone Lake, across Laharte Rapids and the Sour Creek Dome, up a little bit past Canyon to Mount Washington, essentially from rim to rim. And this is what it looks like. Here's leveling being done in Hawaii, another active volcanic place. You've got two rods, they're graduated very precisely. You've got a level instrument in the middle. You read a number over here, you read a number over here, you got the difference. You know how much higher one point is than the other. And then you move this rod ahead, move the gun ahead, and do it again and again and again and again and again. You go from one fixed benchmark for a whole set of temporary setups to the next benchmark, and you know what the elevation difference is between two benchmarks. Those benchmarks are typically something like a half mile to a mile apart. Then if you come back again, say a year later, you do it again, you get a different number, because the second benchmark has gone up or down with respect to the first. Pretty simple, old-fashioned, but it works remarkably well. Here we are in Yellowstone. That looks like maybe Pelican Creek. We're leveling along the road there. We did that again and again and again. The old-fashioned rods had numbers on them. The newfangled ones had a barcode. All you got to do, see, I was the project chief. All I had to do is set the gun on the tripod in the middle, level it up, point it at the rod, and the gun did the rest. I was qualified to do that, and I did that for 20 years or so. We came in 1983 and 1984, and sure enough, relative to that previous survey in the 70s, the one that first discovered the uplift, yeah, it was still going up. So imagine here, this is a profile of uplift. Vertical scale here is in millimeters, so from 0 to 200 millimeters, 20 centimeters. Okay, that's 20 centimeters. And since the 1970s, we found that the middle of that line that went from Lake Butte up to Mount Washington had gone up by almost 20 centimeters at an average rate of 22 millimeters a year. The rate, first rate determined from 1923 to the 1970s was about 14 millimeters a year. So it was still going up, and in fact, on average, it was going up even faster. That's what we thought we'd see. Came back the next year, and there had been no change. 1984, 1985, no change. We're plotting the amount of change during that one-year period along here from one end of the line to the other. There's none. So we had a result. It goes up, and then it went up some more, but it stopped. So uplift is episodic. Nobody knew that before. And we figured, okay, I wonder when it's going to start going up again. Came back the next year, oops, it started going down. So the next year, this is the profile we got, it had gone down. The following year, it had gone down some more, and then more and more and more and more and more, and for 10 years, it just kept sinking at an average rate of 19 millimeters a year. It was going down about at the same rate it had been going up. So now we knew it could go up, it can stop, it can go down. We learned that from the leveling surveys that we started in the 80s. Of course, we didn't give up. We knew it couldn't go down forever. But we wondered, why did it start going down? And there was a clue. The change from uplift to subsidence was accompanied by an earthquake swarm. And that earthquake swarm happened in October 1985, and it was the largest swarm yet recorded in the park. So we thought, okay, there's probably some relationship between that earthquake swarm and the beginning of the subsidence. That earthquake swarm happened here, over in the western part of the park. West Yellowstone would be this corner. And it happened right on the caldera rim. So the caldera had been going up, and then it went up some more, and then it stopped, and then there was an earthquake swarm, and it started going down. Now, if you're thinking sprang a leak, you're thinking like we thought. Somehow the system had sprung a leak. We wanted to understand more about that. So if we just look now, this is a plot of what the center of the volcano was doing. Just look at the upper line here. What the center of the volcano was doing, starting way back in the 1920s. It went up even faster, it stopped, and then started going down. Went down for 10 years. As scientists are wont to do, we wrote a paper, got it published, and we said in 1987 that the uplift might be caused by basaltic intrusions, magma coming into the crust near the base of the crustal reservoir, or we hedged our bets by accumulation of magmatic fluids. I made that in bold because that's a theme that's going to come up again and again. What do you mean by fluids? Well, my point is going to be we never really knew what we meant by fluids. And then we went on to say subsidence might be a response to regional tectonic extension. If you stretch the crust, it's going to sink. Or the release of trapped magmatic fluids. There's that term again. Many years later, 15 years later, Greg Wade and Bob Smith came out with a paper in which they did a much more quantitative analysis involving seismicity as well, and came to a similar conclusion. They said the earthquake swarm and the subsidence they attributed to fluid migration out of the hydrothermal system. It sprang a leak. They pointed out that that swarm in 1985 was unusual. It followed very soon after the reversal from uplift to subsidence. The hypocenters occupied a nearly vertical plane. They had some other unusual characteristics. The focal mechanisms were different than most of the earthquakes that occur in the park. They migrated. They migrated away from the caldera and downward, as if something was moving out and down. And so they called upon migration of hydrothermal fluids outward from the Yellowstone caldera, following rupture of a sealed hydrothermal system. Good explanation. May well be right. We still don't have a better idea. Now, the leveling surveys that I was doing and GPS surveys that University of Utah was doing showed that caldera subsidence and uplift of the North Rim, which I'm going to talk about here in a minute, continued. And then we got a new tool. Now, we'd been doing leveling, old-fashioned technique, old-fashioned surveying. Then GPS came along, we learned some more. Then came INSAR. INSAR is shorthand for interferometric synthetic aperture radar. You can see why we call it INSAR. It's a technique, it's a remote sensing technique. Believe it or not, you can put a satellite in orbit and have it orbit the Earth and image the surface of the Earth and measure how much the Earth might be going up or down. It's an amazing technique. I call it the magic geodetic camera because I've been going out year after year after year with these leveling rods and the tripod and the leveling gun and leveling through snow and hail and wind, benchmark to benchmark, in order to find out that the caldera was going up or down by a few centimeters. Now it's possible to fly over from orbit and do this. Oops, let me back up, and I think, let's see, might have to do it from here. One more time, if I can get that to... Yeah, this is a satellite in orbit. Imagine that there are two radars separated by some distance. It flies over the Earth's surface. It takes a radar image of the surface, and then it takes another one. And then we combine the two. We call it interfering the two images. And there's a lot of data analysis that needs to go into that. There's some magic, but it's all mathematics. And what you get are patterns like this. If the surface is moved toward the position of the satellite or away, you sense that and you get what we call an interference pattern. It's not unlike the interference pattern that you see. You've got an oil slick on a puddle, and it's caused for the same reason. That is that you have constructive or destructive interference between the return radar signal, which travels a certain distance if on the first pass, but it travels a different distance if the surface of the Earth has gone up or down. Now, those of you who are alert said, wait a minute, the satellite moves, a year's gone by. We can deal with all that. We deal with all that, and it's possible to measure using radar interferometry or INSAR, movement, vertical movement, not vertical, technically movement toward the satellite or away from the satellite, to a precision of a few millimeters. Something we can map deformation. We don't have to go from benchmark to benchmark to benchmark, only along one line. We get a picture of it. And of course, people started using INSAR to look at Yellowstone. Let's see if I can make this work the first time. Don't worry in detail about these patterns, but if the surface goes up, you get a pattern of colors that looks like that. If the surface goes down, you get the opposite pattern. Look here, as you go inward, you go from blue, light blue, yellow, red. Here, as you go inward, you go red, yellow, light blue, dark, the opposite pattern. And so you understand how to interpret the so-called interferograms that we get looking at Yellowstone. Here's a generic volcano. We're going to watch it with INSAR. It's going to deflate, and you get one pattern of colors. It erupts a lava flow. It reinflates, you get the opposite pattern of colors. Suddenly we had a tool that could take a picture of how much the Earth had moved. We didn't have to go out with our looking rod anymore. I'm going to try find just a little bit of issue here. So how wide that pattern of color fringes is directly proportional to how deep the source is. You can kind of imagine that. The deeper the source, the broader it deforms the Earth's surface. Smaller amount, but over a much greater area. Shallow source is going to deform it a lot. It's going to push the Earth up or down, but over a smaller area. We can do that sort of analysis mathematically and get at the depth and the size and the shape of whatever's causing the deformation at depth. So we did that to Yellowstone. My colleague Chuck Wicks did it. And at a time when the leveling was showing subsidence, sure enough, that little color blotch there, which isn't very impressive, nonetheless said that there had been more than 30 millimeters of subsidence over here from 1992 to 1993. Who knew that? Because I've been out there 11 of them. Then, yes, next period, 93 to 96, whoops, the color blotch moved from the northeast part of the caldera to the southwest. So it had been going up here, and it was going up here. Then from 95 to 96, to our surprise, remember, it's been going down now since 1985. From 1995 to 1996, the Sour Creek part of the caldera, the Sour Creek dome over between canyon and lake started going up. Now, I don't expect you to tell the difference between that pattern and that, but trust me, that's a little bit of uplift while this part's still going down. We do something new. Sometimes the whole caldera goes up, sometimes the whole caldera goes down, sometimes part of it goes up while the other part of it goes down. It got more complicated, a little more difficult to explain. And then finally, the whole caldera caught up and everything was going up again. The whole caldera pattern was going up, the central part of the caldera. But that didn't last very long because, now you notice the interferograms look a lot better because Chuck and others got better at processing the data and making nice now things look much better, but wait a minute, there's a bullseye up here. That's Norris to first order. We knew from leveling all the way since 1923 that the central part of the caldera was going up and down. Now, Norris was going up, and the central part was going down a little bit from 1997 to 2000. Well, okay, now we got a new thing. We got one source in the northeast part of the caldera, the Sour Creek Dome, another source in the southwest part of the caldera, the Powder Lake Dome. Sometimes one can go up while the other one's going down. And in addition, Norris could go up. From 1997 to 2000, it did. 2000 to 2001, the pattern continued, continuing uplifted along the north rim near Norris. Caldera floor was still going down. That continued 2000 to 2001. The subsidence inside the caldera was slowing down a little bit. I know you can't tell that from the color pattern. You'll have to trust me and Chuck, but that's what those color patterns show. And then in 2002 to 2003, that little red blob there says that Norris was subsiding a little bit and nothing much was going on in the caldera. So now we have to try to figure out what all that might mean. So just to summarize, from 87 to 2003, the central part of the caldera mostly was going down. There was that little short-lived episode of uplift. But the central part of the caldera was going down. The north rim near Norris was going up. So we thought we had another piece of the puzzle. Now we get to 2004. The kinds of rates that have been measured in the past by leveling, by GPS, and by INSAR were 1, 2, maybe 3 centimeters a year. Starting in 2004, things started moving much more rapidly. The central part of the caldera here, both up in the northeast, where at the Sour Creek Dome, and down here in the Mallard Lake Dome, all of it started going up. You see all those fringes, you can think of them as contours. They say that the central part of the caldera is going up, and it was going up 7 or 8 centimeters a year, 70 to 80 millimeters a year. Fastest uplift rate ever measured. At the same time, Norris is going down. Okay, so if somebody presents you with that puzzle and asks you, okay, what's going on? Explain all of the patterns we've talked about so far. Not that easy, especially when you can't get into the subsurface and go see. All you've got is what you see at the surface. So just in that 2-year period, the northeast part of the caldera went up 150 millimeters. The southwest part went up 110 millimeters. In the meantime, Norris was sinking 60 to 70 millimeters. Very dynamic place. Here's the next interferogram in the sequence from 2007, 2008. Pattern continued. It slowed down a little bit. And that's summarized here. During that 4-year period, 04 to 08, caldera was going up rapidly. Norris was going down pretty rapidly. And both things were slowing down in 2010. Then what happens? Another earthquake swarm. And I'll show you that it was about in the same place as that earthquake swarm. Remember back in 85? When we had an earthquake swarm, and for the first time ever, we saw the caldera start to go down. There's another earthquake swarm in a similar place. And guess what? Things changed again. That earthquake swarm is right here, January 2010. Here's the 85 swarm. Earthquake swarms over here tend to change the pattern of deformation inside the caldera. This slide, by the way, from Bob Smith and his students who talk about the details of this swarm in 2010 and the fact that it had characteristics similar to this 1985 swarm. So they wouldn't let me go leveling anymore. In the 90s, they said that's old school. We got GPS, we got INSAR. University of Utah started doing campaign GPS surveys in 87. Permanent stations were installed by University of Utah, USGS, and then by the Plate Boundary Observatory, PBO. You might have heard of PBO. They installed over a period of several years about 1,000 continuously recording GPS stations to monitor the interaction along the plate boundary between the North American plate and the Pacific plate. And Bob Smith, being a convincing sort of guy, convinced PBO that Yellowstone was on the plate boundary. or at least it was close enough that we really needed to include continuous GPS stations at Yellowstone as well. And we're very happy that that in fact happened, because we continue to learn more and more, in this case from continuous GPS. Here are some of the stations. All of the P stations are plate boundary stations. The red triangles are University of Utah and USGS stations. Here's when that earthquake swarm happened in January 2010. And here's the data from one of the GPS stations. And let's just look at the bottom. And this talks about north-south, east-west, but this is up-down. Let's see what happened in up-down. The 2010 swarm happens. The caldera floor had been going up very rapidly, 70 to 80 millimeters a year. The swarm happens and it stops. And then it starts to go down, reminiscent of what happened in 1985. So we had another piece of the puzzle, in this case from GPS. The arrows here show the direction that the ground surface is moving. These are the permanent GPS stations. You can locate them to within a very small fraction of an inch, and over time you can plot which way they move. The red arrows are horizontal motion. This station then is moving in this direction over this time period. The blue arrows are vertical. So this station in Hebgen Valley was moving northwestward, and it was going up during the time period from 2005 to 2009. Next time period, after the earthquake swarm, it reverses. So now we're 2010 to 2012. You see most of the arrows are going in the other direction. Look at that again. Before the earthquake swarm, after the earthquake swarm. So fundamental mode of deformation in the caldera changed. Of course, water in our line. The subsidence continued. It slowed down until very recently. And now we're getting into the very recent past. In middle 2013, last summer, a station near Norris Geyser Basin started to go up very rapidly, more rapidly than we'd ever seen it go up before. Again, this is the north component east, but let's talk about up and down. It started going up very, very rapidly. This is one of the GPS stations among all of those that I showed you. This one is very near Norris. And it was not only Norris that was moving. Here are stations throughout the caldera, all the way up at Mammoth. It started going north. Remember, it's north of Norris. So it's going to the north. Panther Creek is to the north of Norris. It's getting pushed northward. Norris itself, the station is a little bit north of the center of uplift, so it gets pushed south, as does the station at Canyon and the station at Madison. So the episode of uplift, rapid uplift at Norris was affecting stations throughout the park and throughout the caldera. Here's a pattern of horizontal displacements. These arrows show how the Earth, as measured by the stations, moved when this uplift episode at Norris began. Don't look at the blue arrows yet. The red arrows are observations. So the Norris station got shoved mostly to the south. Station at Canyon got shoved to the east, etc. Peter Cervelli is one of my colleagues in Menlo Park, California, with USGS. He did a simple model of what might be causing this uplift. And he concluded that if you had a pressure source that was pressurized within the Earth at a depth of about 8 kilometers, you would get a pattern of surface displacements about like what's shown by the red arrows. And it could represent, doesn't have to, but could represent the very small increase in volume. When we say that among friends in volcanology, we mean maybe because magma was intruded and added pretty small volume, 200ths of a cubic kilometer at a depth of 8 kilometers. That's what Peter said in mid-February of this year. And YBO on that basis issued an information statement. They said that small ground deformation episode had started in north central Yellowstone Park. They said the pattern was consistent with a minor pressurization, 6 to 10 kilometers deep near Norris Junction. They correctly said that similar patterns of ground deformation had occurred before. In other words, don't get too worried. Episodes of ground deformation which occur commonly in Yellowstone and at other dormant volcanoes around the world pose no direct volcanic hazards, nor do they imply that an eruption is impending. Our job at USGS and with our University of Utah colleagues, first and foremost, is to mitigate volcano hazards and provide the public with information about volcanic activity in the U.S. and elsewhere. So first and foremost, we wanted to get the message out that, yeah, something's going on. Similar things have happened before, and there's no cause for immediate concern. That's job one. But for the scientists, including myself, this next statement was very important and very gratifying. These episodes do, however, create a scientific opportunity to better understand the geologic processes at work in Yellowstone and elsewhere. YVO, the Yellowstone Volcano Observatory, and other scientists are pursuing this opportunity and will continue to monitor the ground information closely. That's why I come to work. I understand that my job, first and foremost, is to help mitigate volcano hazards, but I think this stuff is neat, and I'd like to understand it better. And YVO and the folks who wrote this statement, I think, understand that as well. By the way, you can go to the YVO website and get updates, and you can go to the data from the continuous GPS stations. You can look at that daily. I can show you the link if you don't already have it. So, obviously, we continue to do INSAR. We got a new satellite, thanks to the Germans. The Germans launched TerraSAR X. It operates at X-band, a shorter wavelength than C-band. All of the interferograms I showed you so far were at C-band. Because you're operating at a shorter wavelength, you get a little better precision, a little more resolution. And here is an interferogram for the period. First of all, the other nice thing about this particular satellite, instead of coming back over the same point and revisiting it every 35 days, it does it every 11 days. So you can get a more detailed time series. And you can get resolution in one mode of as good as 25 centimeters, a quarter of a meter. You get resolution like this on the ground surface in orbit to find out how those pixels are moving. It's really remarkable. It's nothing like we used to do with our lovely clouds. So here is one of those images, October 2012 to June 2014. And there is the rapid uplift at Norris that we talked about earlier. 5 centimeters of uplift centered there near Norris Geyser Basin. A little bit of caldera floor subsidence. Norris is going up, caldera floor is going down just a little bit. Peter Cervelli pointed out that if you plot the amount of horizontal movement and the amount of vertical movement at the various permanent GPS stations, and then you fit a model that said that the source might be about 8 kilometers deep with a small volume increase, the model fits the data pretty well. But we're missing data at these distances. The distances between about 5 and 15 kilometers, there just weren't any permanent stations. And I thought, great, because I had been coming, since they wouldn't let me level anymore, I'd been coming each summer and putting out temporary GPS stations at holes in the permanent network. We had installed 9 such stations, and 2 of them were in a very good place. These 2, at these distances, if we could come back and reoccupy them, we could see how well Peter's model fit those data, and that's what we got to do. Those stations, 9 stations, 5 of them went in 2008. They're the yellow stars. Another 4 went in 2009. They're the red stars. And the 2 that turned out to be in a good place are Grizzly Lake and Barrow, because the center of the uplift, it's not shown. This is a different time period interferogram. Center of uplift was just about there. So Grizzly Lake should have moved that way. Barrow should have moved that way. We came here in March of this year. We put out our stations, which look like this. There's just a pin affixed to what we hope is stable bedrock, a little antenna that looks like a frisbee, a solar panel to power the station, and something you can't see here, which is a little GPS receiver. We try to camouflage everything so that we're unobtrusive. Here's that pin in bedrock. Here's the antenna. There's a GPS receiver hidden in there. We deployed them for about 4 days. Snowing, or it had snowed at Grizzly Lake, one of the 2 important stations. Deployed that station. We in fact put out 5 of them, and the results we got were consistent with Peter's model. The 2 most important stations, Grizzly Lake, moved like that, Barrel moved like that, just like you'd expect from the source center just north of us. So the data fit the model, and the model fit the data. And Peter pointed out that based on those observations, Grizzly Lake and Barrel were going up about 3 centimeters a year, and that the data were consistent with the previous interpretation. It was very gratifying. You never get to take a break in this business, because as soon as you think you know what's going on, something else happens. So we were here in late March, early April, and on March 30th, there's a magnitude 4.8 earthquake in the vicinity of Norris. It's maybe somewhat surprising. That's the largest earthquake that's occurred in Yellowstone Park since sometime in the 80s. I pointed out that magnitude 7.5 that happened in 1959, magnitude 6.1 that happened in 1975. Those are tectonic earthquakes, and they have an origin in the tectonics of the region. The earthquakes that occur within the park almost exclusively are very small, and the majority of them, or a significant fraction of them, occur in those forms. These earthquakes are magnitude 0, 1, 2, 3. The magnitude 4.8 that happened on March 30th of this year was the largest since the 1980s. And not surprisingly, this is what was going on at Norris on March 30th. It had been going up rapidly, and after the earthquake, it started going down. So an earthquake, once again, it changed a very distinct, it caused a distinct change in the pattern of ground information. That same pattern was accompanied by the beginning of uplift inside the caldera. These are vertical motions plotted here for stations at Old Faithful, White Lake, Hayden Valley, Deer Lake. You see sometime in mid-2013, before that earthquake in March of 2014, the caldera, which had been subsiding, now started to go up. So once again, we were seeing a reversal related to a significant earthquake. That reversal was seen throughout the park. Near Old Faithful, the caldera started going up. Northeast corner of the park on the seismic resurgent dome started going up. The arrows here are the earthquake. Same is true here in Hayden Valley. You see the distinct change from caldera force subsidence to uplift. And also Norris Geyser Basin, as I showed before. It had been going up rapidly, boom, earthquake starts going down. Here's an interferogram that shows that pattern in more detail. Uplift within the caldera at a rate of about 12 centimeters a year. It's very rapid. We had not seen that during the previous 2 and 3 decades with other techniques. Norris is going down a little bit, not a little bit, a lot, 15 centimeters a year, while the caldera floor is going up, Norris is going down. And so now I'm going to put a whole lot of words on the screen, which is never a good idea, but don't worry about it. What the words are going to do is kind of summarize what I've been saying, because it's complicated. 1923, the first leveling survey. To 1970s, caldera had gone up almost a meter. Wow, Yellowstone goes up. We didn't know that. Then we learned that sometimes it goes up, sometimes it stops, sometimes it goes down, but generally uplift dominates. There are 2 primary deformation sources where this deformation is concentrated: in the middle of the caldera and near Norris Geyser Basin. Norris generally goes down while the caldera goes up. In one case, when both the northeast and southwest parts of the caldera had been going down for a decade, imagine those 2 resurgent domes are both going down. In one case, Sour Creek Dome started going up while the Mallard Lake Dome was still going down, and then the Mallard Lake Dome caught up. That's an important clue, we think, about what's going on under the surface. You get a whole lot of earthquakes, but they're shallow, and about half of them occur in swarms. You don't get earthquakes beneath Yellowstone caldera deeper than 3 miles, or 5 kilometers. Why? Because deeper than that, the crust is too hot to break. It doesn't break, it moves out of the way. You get outside the caldera, you get earthquakes down to 15 kilometers or more, because the crust there is colder. You get tectonic earthquakes like the big ones we talked about. You get earthquake swarms which have been associated with fluid migration, like the 85 swarm and maybe the 2010 swarm. And maybe you get earthquake swarms because magma is intruding beneath the caldera. We'll talk about that more in a minute. The beginning of subsidence in 2 cases was triggered by earthquake swarms out near the northwest caldera rim in 85 and 2010. And there was a Yellowstone Lake swarm, which I neglected to talk about, in which the earthquakes migrated not outward and downward, but rather inward and upward. And Bob Smith and others at the University of Utah attributed that to an intrusion, an upward intrusion of, once again, a fluid. The question is, was it magma? Was it some hydrous fluid, some form of water? What fluids are we talking about? The most recent episode of uplift started in 2013 at Norris. It turned around abruptly after a magnitude 4.8 earthquake at the end of March of this year. And those earthquakes weren't unusual. Utah says, yeah, they're typical swarm earthquakes. It's not like they're something unusual related to volcanic activity. Let me skip through the rest of these things. We know a lot about Yellowstone. We know how much CO2 is released. We know that CO2 is coming from magma at depth. We know about how much magma has to be degassing to produce the amount of CO2 that's coming out of the park. The answer is about 0.3 of a cubic kilometer a year. We know, therefore, that there's a large reservoir of magma under Yellowstone caldera that's supplying that CO2. We know the proportions of gases coming out, and the amount of CO2 is consistent with a source in a magmatic reservoir. We know how much heat is coming out of Yellowstone, and it turns out that the amount of heat coming out of Yellowstone is consistent with cooling the volume of magma that would produce the amount of CO2 coming out of Yellowstone. It fits together. And then, if you're going to talk about fluids other than magma causing deformation at Yellowstone, there are plenty of fluids. There's, of course, water. Water is given off by magma as it cools. So is CO2. And of course, then you have the hydrothermal system, which is fed in part by meteoric water. You've got lots of sources of fluids if you want to invoke. So Chuck Wicks and I came up with this model that we published in Nature in 2006. Remember that one episode when the whole caldera had been going down and this part started going up before this part went up? We said that suggests that there's a conduit system for magma, and it's centered closer to the northeast part of the caldera than the southwest. Magma is accumulating here, that either magma or gases and fluids released from that magma sometimes migrate from the primary source laterally over to the Mallard Lake Dome in the southwest part, or up toward the Norris Geyser Basin. That there's essentially a valve here. Sometimes it's open, sometimes it's closed. When it springs a leak and fluids can leak out, Norris goes down. For reasons we don't understand, when Norris goes down, the caldera floor tends to go up. And that explains, in a very qualitative way, which is another way of saying an arm-waving way, a lot of the observations that I told you about. So, what questions are still out there? I'm almost finished, and I'm not going to answer them, but I'm going to pose them. The big question is, what are the fluids or fluid responsible for ground deformation? Why is Yellowstone going up and down? Is magma getting intruded across the uplift? If so, why does it sometimes go down? Does the magma leak out somewhere? We don't think volcanoes like Yellowstone work that way. Is it going up because the hydrothermal system is pressurizing like a pressure cooker and then springing a leak? Well, maybe, but all that heat is coming from magma. What's the role of magma? So is it magma? Is it fluids that we know are released from magma as it cools? How do we answer that question? There's a very interesting experiment that has gone on this summer and will continue to go on for the next couple of years at St. Helens. So this is where I live. It's a National Science Foundation sponsored project. It's called iMush, which strikes me as a very nice way of saying imaging magma under St. Helens. The idea is, we know because St. Helens has erupted twice since 1980. It built a lava dome from 1980 to 1986. It went asleep for a while, built another lava dome from 2004 to 2008. We know there's magma down there. We know it has to get to the surface, so it has to come up through some conduit system. Let's see if we can image, is get a detailed model of what the plumbing system looks like. Think about the volcano. Have a plumbing system like you have in your house. It has to get magma from deep within the earth, up into the crust where it spends some time, and then up to the surface to build a lava dome or feed explosive eruptions. So some of my colleagues came up with imaging magma under St. Helens, IMUSH. And that's going on right now. They deployed 1,000 seismometers and then set off some shots around the periphery of the volcano, that is explosions. And those waves set off by the explosions travel through the earth, but they're affected by differences in the earth's structure. Some rocks transmit seismic waves faster, some slower. If you've got fluid, if you've got a magma down there, it can't transmit certain types of waves. And they think they can get a picture of the magma plumbing system under St. Helens by analyzing those seismic data. And they're doing some geophysical work as well. Very elaborate experiment. So one night I came up with the idea. We need to do a similar thing, Yellowstone, to find out, finally, once and for all, what fluids are we talking about. But you gotta have a catchy name, right? So I thought, this is kind of what the subsurface of Yellowstone looks like. We know there's a magma reservoir. It's rhyolite. We know that it's fed at great depth with the salt. The salt interacts with the crust. It forms a silicic reservoir. The reservoir is giving off some gases and making some earthquakes. What could we call such an experiment? And I came up with imaging fluids under Yellowstone. IFUI. Well, I thought about it and I thought, that might not be the best name. So I kept thinking about it and I came up with Wi-Fi. Wi-Fi is Yellowstone Fluids Investigation. That's how far I've gotten. I came up with the name. Now I'd love to be able to pitch this to scientific colleagues and eventually to a funding agency, because I think it's the next big question to answer in Yellowstone. What are the fluids that are causing these remarkable ground movements, up, down, in, out? North goes up, caldera goes down, vice versa. And we know magma's involved. We're pretty sure gases are involved. We're pretty sure the hydrothermal system is involved. How's it all work? Let's go look. And we know some of the things we would need to do. Some of the things are already being done. Very detailed seismic work, such as being done at the University of Utah. Gravity, Utah's been doing gravity for several decades. We need to do more gravity because if you think about it, if you intrude magma, you've added mass. If you've added mass, you've increased the local gravitational field. You measure gravity well enough, frequently enough, you ought to be able to see that. If the ground surface goes up, gravity will decrease a little bit because you're farther from the center of the earth. You correct for that. If gravity's gone up even more, you know you've added mass. If the ground surface goes up, and you do the correction, and there's been no gravity change, you haven't added mass. So maybe you pressurize something without adding mass. And you can go through that thought process for subsidence as well. So a combination of geophysics, including gravity, seismicity, deformation, because I want to still be involved, I think is the way forward at Yellowstone. And with that, 5 minutes over my time, I'll stop and take as many questions as you want to ask. Thanks. Now, I said that I first worried that you guys might be a high-end band, a group of outlaws. I hope you'll be kind with your questions. I see one back there.
With all of this bending, are there any surface evidence of cracking or sparring?
Good question, which is that because the surface is deforming, do we see surface cracking? And the answer is no, not at the surface, that the strains are small enough that we don't see surface fractures. The rates of deformation are low enough in general, the stuff I'm talking about. Occurs a few centimeters over a matter of a year. The Earth's crust is able to flex at those rates and not break. But Yellowstone makes a lot of earthquake storms as well, and so locally strains do exceed the breaking strength of rock in earthquakes. Those don't seem to be very directly related to the kinds of broad uplift and subsidence methods. Yes, sir.
Sounds like what you're describing, sounds like gastrointestinal rumbling.
Okay.
But I do have one question, a serious question. Can you go back to one of your slides that shows the data on up, down, north, south, east, west movement? Pick any one.
Any particular time period?
No, there you go, right there at the bottom.
Something like this.
Yeah. There's both discontinuities and missing data on there. Can you explain what's causing that?
Yeah, I sure can, and that's a good question. Why are there data gaps, and why are there outliers? The data gaps in this case, we simply had a loss of telemetry, and the telemetry from, I think this is Norris Observation Station, simply was down for this time period, and somebody had to go to the site and fix it.
Battery power or something?
I don't know what the reason for the outage was. There was a loss of telemetry. And then I think you were asking about some of these outliers.
Yeah.
The nature of the data. There are various effects that can cause such anomalous data. You can have well, first of all, it's pretty miraculous, if you think about it, that you can do this. You can put out a station and measure where it is using satellites that are within the Earth's surface to within a very small fraction of an inch. To do that, you have to model how much water vapor there is in the atmosphere, because those GPS signals come from varying amounts of water vapor. You have to model the ionosphere, because the ionosphere also affects the GPS signals. And you do that, and most of the time end up doing pretty well. But there are outliers.
On the east-west graph there in the middle of 2006, it's what I would call a discontinuity. To the right,
Here.
Yeah, and that looks like somebody changed the rules, reset calibration or something.
You know, I think you're right. I see it in the east, and I think I see it in the other, and I don't know the answer to that.
Set data starting.
Yeah, I'll defer to colleagues who is doing. I don't know the answer to that particular question. Yes.
So before a major eruption of the caldera, I assume displacements would be multiple times greater than anything we're looking at now. I don't know if you can comment on that.
The question, in case you couldn't hear it, was that presumably before another major eruption in Yellowstone, or any kind of eruption, but a caldera-forming eruption in particular, we would see movements of the ground surface much, much larger than this. And we certainly think so. Models would suggest that you would have to trigger eruption of a large volume of magma. Might already be stored in the crust, but you'd have to trigger it somehow. And you would have to trigger that perhaps by an intrusion of fresh magma from below the salt. That would pressurize the system, increase its volume, and we would expect to see much larger ground deformations than we see now. We would expect to see very intense seismicity. We would expect to see changes in the amount and the proportions of various gases coming off the magma and released to the surface. I said we think so because, of course, we've never monitored a caldera-forming event. We monitored a wide spectrum of volcanic eruptions, and the accumulated knowledge from monitoring all those eruptions is that in most cases, the precursors tend to increase as an eruption nears. Just like there are exceptions and little outliers to the data, there are exceptions to that. Even some well-monitored volcanoes erupt with little or no warning. And they're not common, they're outliers, but it sometimes happens. All of the evidence would suggest that if you're going to have a very large eruption in a place like Yellowstone, that you're going to have very large precursors as well.
And what would we do with that?
What would we do?
Given I mean, I was looking at the situation, it sounds very interesting, but given it's going to cover 3/4 of the United States, kill people within 500 miles.
Next question.
Exactly.
Well, I'm not sure how to answer that question except sort of
increment.
Well, I was thinking, because you said your primary task was, could you repeat what the primary task
To
was?
mitigate volcano hazards and the threat to life and property.
Right, so how would we do that in this case? Is there a plan, or we just kind of hope for the best?
We're still being recorded.
Do you want me to turn it off?
You know, let's face it, in the event of a caldera forming eruption, it's very hard to mitigate those kinds of effects. What we would hope to do is recognize as early as possible the precursors that something unusual is going on, follow those precursors as they intensify, issue a series of statements providing information, and then eventual warnings of specific potential outcomes over specific time periods. The kinds of things we've done successfully at St. Helens at various levels of the ocean. Remember that most eruptions in Yellowstone are not caldera-forming eruptions. A lot of them are effusive basaltic eruptions. That's why you don't see a big hole in the ground, of course. The entire caldera that formed 640,000 years ago has been buried by lava flows. Those were mostly non-explosive eruptions. Might have been explosive activity associated with some of them, but basically, thick, pasty lava oozed up out of the ground and buried the entire caldera. A lot of the eruptions in Yellowstone don't even involve magma. They're hydrothermal explosions. You form things like Indian Pond, Mary Bay, very good example. Now, those would be pretty darn disruptive too. And we're not sure in those cases, the hydrothermal explosions, that we would see precursors. There have been hydrothermal explosions around the world that seem to happen with few, if any, precursors. So to answer your question, we would provide as accurate, timely information as possible, both to the land management agency, because remember, the USGS is not going to tell anybody to evacuate Yellowstone Park or the western United States. We're going to provide information to the relevant land management agencies, the Park Service, local law enforcement, others, because they have to consider a lot more than the scientific data. They have to consider, well, what happens if we try to get everybody out of the park within a few hours? Traffic accidents, we're going to block the road. They have to consider this. So, to answer the question, we would provide as much, as timely, as accurate information as possible to the relevant agencies, relevant land managers, and hope that the next caldera forming event doesn't happen anytime in the foreseeable future. It's not overdue. I'm sure you've heard on the supervolcano stories. My gosh, there have been 3 caldera forming events in the last 2.1 million years ago. 2.1 million, 1.2 million, 0.6 million. Sounds like it's overdue. No. Those dates, those kind of, we know that these systems are not that regular. And even that sequence of numbers gives you a leeway of 100,000 years. 100,000 years is a long time. And in the past, caldera forming events prior to the 3 at Yellowstone, the events that have happened over the last 15 million years, along what's now the Snake River Plain, which are now all buried by the salt. There were periods of several million years when there were no caldera forming events we know about. So it's not as if there's any reason to think the next caldera forming event is around the corner. But these things have happened in the past and not happening in the future. But we're talking timescales that are extremely long compared to anything that we're ever prepared for. Okay, how about that one?
Is there any evidence that it is slowing down or cooling at all?
No, the question is, any evidence that the system's slowing down or cooling? No, I think the evidence to the contrary is that Yellowstone is just as active, just as alive and well as it has been any time over the last 3 million years at least. It's just that this is how it behaves in middle age. It goes for 100,000 years or more, sometimes a few million years without erupting. But that's its pattern, that's its mode of operation. No evidence to indicate that we're running out of energy. System's alive and John?
Yeah, I'm kind of curious, when you see one side going down and the other side going up, obviously something's moving underneath. Would you care to speculate, is that mostly gaseous or mushy or molten? What is moving around down there when those sorts of things are moving?
Well, I think if we fund Wi-Fi, we could probably answer that question. I don't know, and quite frankly, over my career, I have published papers that have suggested any and all of those things. There are time periods when the data are consistent with the idea that what you're doing is you're pressurizing the hydrothermal system. Obviously, there's a lot of hydrothermal system activity in Yellowstone. Puts out a tremendous amount of heat. We know from studies both at Yellowstone and elsewhere at other hydrothermal systems, some of which have been produced for energy, that the system tends to seal itself up at a depth of maybe 5 kilometers or so. It's hot enough, and there are enough minerals that are crystallizing that any fractures that are there close up because the rocks can flow, and you get mineralization, you get crystals forming that clog up all the pore space, all the fracture space. And so you can pressurize the hydrothermal system. And you can pressurize it to pressures that exceed what we call lithostatic, or exceed the weight of the overlying rock, and you can cause overload. Well, eventually, in the earthquake swarm, you create some new permeability. The system that you pressurize starts to leak, and you get some stress. That seems to explain some of these episodes, but not all, and it doesn't explain in any great detail all of the complexity that I talked about. The real answer is undoubtedly more complex than any one thing. It's not magma or hydrothermal or hydrous fluids or gas. It's probably a combination of all those things interacting with a very complicated and fractured crust in a very dynamic environment. But the first order question, how much of the uplift in particular is caused by intrusion of magma into the middle of the crust? The way to answer that question is to do the kinds of studies that Bob Smith and his students have been doing at the University of Utah. That is, studies of gravity, changes in the gravitational field over time during periods of both uplift and subsidence. There has been an interesting result that was published by one of Bob's students that said during a period of sustained uplift, after you correct for the fact that gravity would have gone down a little bit because you're lifting facilities, after you do that correction, there was an increase in what we call muove gravity that you could attribute to an increase in mass. So it looks like during that period of uplift, magma may have accumulated. Then there was a reversal, and there was a period of 10 years of subsidence. They continued to measure gravity, and after they corrected for the gravity increase because it subsided and got a little closer to the center, there was no residual muove gravity change. And so they published a paper saying it looks like an intrusion of magma that caused a mass increase, and then that magma stalled and it cooled and it lost gases and depressurized a little bit, but didn't change the mass. And it caused subsidence as you depressurized the system and lost those gases. It makes good sense. May well explain a large part of what I'm talking about. But it doesn't explain the complexity. It doesn't explain why, in some cases, part of the caldera floor can be going up while the other part's going down. And in general, the caldera floor goes down when the crust goes up. We're not there yet.
Is there, with these lifts and drops, are there subsequent warming and cooling of the surface soils and cold water reservoirs, lakes, tributaries, and such?
Boy, I wish there were, because that would be a prediction. If the model is that these mineralization processes and the flow in hot rocks that closes up all the permeability, that causes a self-sealed layer at the very base of the hydrothermal system, maybe 5 kilometers down. That's the idea. Then you accumulate magmatic fluids. After all, magma underneath is still cooling, it's degassing, giving off water, it's giving off CO2, it's giving off other gases, it's giving off chloride. And then you spring a leak, Wouldn't it be nice if you saw an increase in some of those things coming out of the surface a short period later? That experiment's been done, and the answer is ambiguous. We've been monitoring the amount of chloride coming out of the rivers that drain Yellowstone for decades. That was done because through some math, you can, if you know the total amount of chloride coming out, you can calculate the amount of heat being given off conductively from magma. And that's the basis for the estimate I said, 4 or 5 gigawatts. Chloride was being monitored in the rivers after the earthquake storm in 1985 that caused the reversal, or at least was related to the reversal from uplift to subsidence. People went out, they looked to see if the amount of chloride went up because the system is probably, the self-sealed layer might have probably. They didn't see an increase in chloride. On the other hand, Bob Fournier, the guy who came up with the whole idea, I mean, sort of Mr. Yellowstone hydrothermal system, points out that it's really complicated between the self-sealed layer at 5 kilometers depth and the surface. And no one knows what the time scale would be for the release of chloride that might have been released due to fracturing that occurred in that earthquake storm. And maybe we'll see an increase in chloride 100 years from now related to what happened in 1985, or maybe it'll never get to the surface because it's been being diluted by all of the meteoric water that gets dumped. So we didn't see the smoking gun. It would have been nice, but that doesn't mean that the mechanism wasn't a fracturing of the deep hydrothermal system. We didn't see anything get out in the short term, but maybe we just couldn't see it.
In the most recent earthquake there north of Norris, the 4.3, it wasn't clear to me which nature you were putting it in, whether it was in tectonic or whether it was in the normal Yellowstone. And some people have actually gone so far as to suggest it was an aftershock of a Hebgen earthquake, which I found a little hard to believe. But I'm kind of curious, where would you put it and why?
Yeah, I skipped over that part. What I meant to say is it looked like a normal Yellowstone earthquake, not part of the swarm. It had a focal mechanism that was normal fault. It's as if fracture happened like that. It was not unusual. It was, and I'm just talking about what University of Utah has said. It was a typical small tectonic type earthquake for Yellowstone. When you do focal mechanisms, and you're a volcanologist, you know, rocks can break like this. They can break like this, strike slip, as they do in San Andreas. Various permutations of that. They do this, then we get really interesting. You get an opening, then you intruded something into that fracture. You don't see that very often. And we've never seen it in Yellowstone. But the University of Utah has never seen it.
Way out of question here, but have, with all these subtle changes going on, has there been any change in wildlife location, densities, or movements that you can tell?
Not that I'm aware of.
You always hear how they're sensitive to what's going on.
Yes. That's right. Not that I'm aware of, but I'm not entirely sure I would be made aware of that. Of course, there's a lot going on with wildlife in Yellowstone in terms of changing habitat and changing development and visitation patterns. I have not heard that kind of report that wildlife have reacted in some way either to seismicity or the ground deformation.
We have a ring of fire that goes all along the western side of the hemisphere. And is there any correlation of activity from one place to another? Or does it flow up the stream or downstream to give you some kind of indication of calculation for the Earth's crust rather than Yellowstone itself?
Not that anyone has been able to demonstrate in a convincing way. People have looked over the years for that sort of a pattern. You know, when at plate boundaries where you have lots of volcanism, is there any evidence for migration in one way or another? Is there any evidence for external forces triggering volcanic eruptions, earth tides, ocean tides, any number of things? And there has never, to my knowledge, been a compelling case made for a causal relationship between one eruption and the next and the next. It's true that sometimes you get what seems to be a clustering of volcanic activity in one part of the world. I think it's the case if you take the broad view and look at those statistics, you can't convincingly demonstrate that those sorts of influences occur. Now, there are always exceptions. There are a few cases, I can't cite you the date, but I know there are cases where big tectonic earthquakes, magnitude 7 and 8 earthquakes, have been followed very shortly by volcanic eruptions. Makes sense. And I think it's the case that volcanic eruptions, large volcanic eruptions, which do cause the earth to deform, have sometimes been followed by large tectonic earthquakes. But it's not a compelling pattern that you can use in any sort of predictive way. I guess that's the best answer I can give. It's not the norm. There might be cases which are outliers. Sometimes it happens, but it's not the norm.
I'm going to go on with one more question. Do you follow at all the ocean volcanic action?
It's not a primary responsibility of ours at Cascade Volcano Observatory, but of course I'm aware that a lot of years volcanic activity is occurring under the ocean.
Does that come into the
Well, the Earth is
Yeah.
it's a big heat engine, isn't it? And you know, just in my lifetime, plate tectonics has become understood. Let me give away my age. I was born in 1951. Plate tectonics emerged in the 1960s when I was in school. And we didn't know that the Earth was composed of rigid plates that were moving and colliding and causing mountains. That's all happened just in my lifetime. And so, yes, all those things are related. Mid-ocean ridges are creating oceanic crust. They're causing oceanic crust to move away from those strikes. And in some places, oceanic crust is colliding with magmatic crust and subducting. And where that happens, the subducted plate tends to, physical processes go on that including becoming heated and losing water, and that water rises and lowers the melting point of the crust, and you make magma, and you make things like the Cascade Range. It's all related, but it's a very complicated system.
Well, I think you've been a very good audience, and I think very interesting talk. I won't put down the point of saying, well, will he sleep well tonight? But I'll tell you that I'm not going to worry about Yellowstone in the slightest.